Good evening. I'm Professor Huffman with Marshall University. We're here this evening to do a little review for the Civil Engineering Materials portion of the FE exam. We've got a classroom that I'm speaking in front of, and we've got some slides we're going to go through to start with. I've got two separate presentations I'll pull up. One's material concepts and aggregates, and then a second one dealing with Portland cement concrete, and asphalts, and we'll go through those. It's more of a review session for what we go over in class, so that we bring all this back to the front of your brain. There will be a few questions, but not really so much questions here, but really going back through and make sure you understand all the things. If you have a question, please ask. Please speak up so you're on the microphone, so everybody else that's watching this and listening to this can understand what the questions are. After we do those two things, we'll take a quick break. And then I've got some sheets that are directly out of the review manual to pass out to you so that you're aware of where the material is on materials. And unfortunately, there's not a section in the book like there is for other things like geotechnical engineering or structural engineering or statics or things like that. It's kind of intermixed because materials is involved in everything. So it's here, there, and everywhere. So I've got those specific pages that deal with those kind of things copied so you can become familiar with what's in the book. And that's the key to the exam, is know what's in the book and know where things are at. Luckily now with the online testing, it's an electronic searchable database, so you ought to be able to go real quickly and find things maybe you don't know where they're at by doing that search through that process. So we'll get started in looking at materials and aggregates. Everybody remembers the stress-strain curves. This is the kind of question you'll see on there that will say, tell me which one of these curves is typical of steel, or which one of these curves is typical of soft rubber. They're probably not going to try to make you distinguish between an aluminum alloy and a concrete or something of that nature, but they will on some of these other ones that are a very rigid material like glass versus the rubber, the soft rubber, which is diagram E we see there. Got to know all your terms. That's the secret to this part of this exam, is knowing your terms, knowing what elastic behavior is. That elastic behavior is we can load and move up the stress-strain curve to the elastic limit, and then as we let that load off of the sample, stress off of the sample, it returns back to the same exact shape. So that's our definition of elastic behavior. What we see here on the screen right now is a linear elastic behavior. Returns to its original position. And all we've done is we've loaded and we've stretched those atomic bonds. We haven't deformed them. And that's why it goes back to its same exact shape. We can have the linear stress-strain curve, or we can have a nonlinear stress-strain curve. So it can be a curved surface. Many people think because it's curved, that means it's not elastic. If I load a nonlinear elastic curve up and unload it, it'll return back the same shape. Therefore, it's an elastic curve. We can look at different definitions of the modulus of elasticity. We classically think of it as the initial tangent modulus. We've got a straight line portion coming off our origin, but there are other modulus of elasticities out there. We've got secant modulus, which is just between any arbitrary point in the origin. Somebody will say, give me the secant modulus at a certain strain, certain stress. Locate that point, connect the two, get the slope of that line, and that's the secant modulus. Chord modulus is between any 2 points. A lot of times that's defined by by strain. And you define your 2 points, put them on the curve, draw your line, and you get your chord modulus. Tangent modulus is at any point on the curve. Get the tangent to the line at that point, and get the slope of the line. You've got the tangent modulus at that particular point. And you'll call these out at those particular points when you refer to them. Modulus elasticity, Young's modulus, E, stress over strain. We've been dealing with stress over strain our whole careers here. Pretty simple and straightforward. Dealing with the linear portion of the curve, we're typically thinking of things in homogeneous and isotropic conditions and a linear elastic material. typical values you'll see out there. That's something they can ask you. Here's a set of modulus of elasticity values. Which one's the correct one for steel? Which one's the correct one for concrete or whatever the material might be? So some of the questions can be that fast. And if you know it, and you're in great shape. If you don't, maybe you can search it and look it up real quick. If not, process of elimination, try to get rid of 2, and then you're down to 50-50 chance, right? Poisson's ratio, again, we've all worked with this. We're looking at materials and how they change in dimension based on loading. If we take a material, a beam or a piece of metal, and we pull it in tension, we're going to get an elongation in the long axis, and we're going to get a reduction in its diameter. Conservation of area or conservation of volume there. Problem that they could give you would be here's the load on this column, compressive load on this column. How much did the column increase in diameter? And go through the process of figuring out what your strains are, your stresses are, figuring out what your strains are, and then use Poisson's ratio to back calculate out what value of diameter change you would have. Yes, sir. When you're doing this exam, you'll have 2 screens. One screen will have the actual FE reference manual in it. It won't be a physical copy, but it's an electronic copy. And on the side of it, it's got search modes. So you can do search when you say you didn't know what Poisson's ratio was. You can type in Poisson's ratio, and it'll pull up all the locations in that reference manual that have Poisson's ratio listed. Sure. Yeah, it will. Yeah. So that from the standpoint of being able to be Google-like, if you will, and be able to search for things, you can search for things in the book that way. And some things like searching Poisson's ratio, I think would be dangerous as can be, because I bet it's in there over and over and over. Other characteristics or other terms like effective stress from a soil mechanics question probably wouldn't be in there that many times, or it would get you into at least the geotech section. So you can do all these searches real quickly, and it'll bring them all up, and you can go down through there and find which one you think may be the prime one you want to go to help find your solution. So it makes it, most students, modern students like that, do that electronic search. Us old folks would rather have the book with a nice glossary at the end of it. We could have elastoplastic behavior. And they're going to ask you more of the common kind of questions about stress and strain, modulus elasticity, and modulus of resiliency and toughness and things like it. They typically, I haven't seen them get a lot into elastoplastic behavior. But those exist, and they're actually more common than your linear elastic materials. The transition point from going from the elastic condition to a plastic condition is that elastic limit. And you can get different levels of elastoplasticity in materials. From a perfectly plastic, that it'll go up to the elastic limit, and it'll be a horizontal line to some form or fashion of some kind of slope above that, depending on the material type. When we're looking in that elastic region, we're just stretching the atoms, and they're bouncing back if we don't go past that elastic limit. Once we go past that elastic limit, we're starting to tear things apart and rearrange their shape and their organization, and they will not return back to the original state that they were in. We start getting, the bonds are slipping past each other. We're not going to return back to that original shape. We're going to have some residual strain in there. We see that we don't have the same slope by any means. Our elastic limit's going to, elasticity is going to keep increasing. When we get that plastic limit, we're going to see shallower slopes to horizontal surface on our figure. When you got something that's brittle, and these are great questions, if you've got a brittle material, will it have a plastic zone? No, it won't. Ductile materials undergo appreciable plastic deformation to failure. There'll be questions that can ask you those kind of things to see what you know about those stress strain curves. A little bit about the different type behaviors. If we look at something like curve figure A there, we can load up the material, go past the elastic limit and we relax the load, our rebound and our initial loading are going to be in the same slope. They're going to be in the same slope for that material. The plastic strain that remains is because the material plastically deformed as it went to the right. That's there. We can't get rid of that. So we've got the elastic strain portion of the curve, and we've got the plastic strain portion of the curve. B's, that perfectly plastic, goes up, goes completely horizontal. If I let the stress back off here again, it's the same slope as my loading curve. And we've got some elastoplastic with strain hardening. We're not horizontal. We're some form of an angle, light slope going up through there again. Unload it. It's going to come back down, and each one of those will have plastic strain that is there permanently now. It is there permanently now. We can define strains, and I have seen a few questions related to this. We can define our yield stress, our elastic limit by different methodologies. We can do offset method. We can do extension method. I'm just to be familiar with which way each of those are determined. When you're doing your offset method, you're offsetting by the percent strain you're interested in and drawing a line parallel to your initial tangent, or initial slope. And wherever you intersect the curve at is where the result of what you're looking for is. You can do it with the extension method. You go over it, but you go vertical. You go straight up. You don't match strain, the slope of the modulus elasticity curve. So two different ways of defining those points. Everybody's seen this in the materials class. Make sure you know where all those points are at. Make sure you know where all those points are at on this diagram. Make sure you know what the difference between the proportional limit and the yield point is. Make sure you know the difference between true stress and strain and engineering stress and strain. We deal with engineering stress and strain strictly when we start doing all our junior and senior level classes, because that's what we care about and that's what we want to design with. But there is a true stress strain curve that keeps on going up as it goes to the right. So make sure you know all those different points in those terms, because that's one of the things they like to ask is some of those term questions about whether you know these points on the curve. Proportional limit, transition between the linear and nonlinear. Elastic limit, transition between the elastic and the plastic. Those are not the same points. They are not the same points. Yielding, when you have a continuing increase in strain with little or no increase in stress, that's when you're yielding. Ultimate stress is the maximum peak on your engineering stress strain curve. Of course, that's what we're after a lot of times, is the ultimate stress strain. We'll back off of that for design purposes. Rupture stress, pretty obvious what that is. Brittle materials, they undergo little elastic deformation. Good examples are glass or concrete. They give you no warning. They load up, they don't quiver, they don't shake, they just pop. Where you have ductile materials, they do give you some warning. The steel will start to yield, start to neck. If it's rubber, you're going to see a lot of compression, and you know you're getting towards failure because it's giving you those visual signs and those strain indications. Viscoelastic, I'm going to pass right past this because we haven't done it in the past. These are good questions that you see on there real quick. Modulus of resilience, toughness, knowing the difference of what those are. Toughness is the energy required to fracture the material, so it's the entire area underneath the curve. Know the difference between high strength and high toughness. High toughness means you have a large area under the curve. High strength means your stress strain curve reaches a higher peak. They typically don't go together. They typically don't go together. So you can get a question. It's like, is this material tough? Have a high toughness? Does this material have a high strength, or does it have both, or does it have neither? I mean, that could be the question. And if you're looking at, and they've got two curves here. Maybe maybe they'll call one of these A. They call one of these A, and they call one of these B, and they'll say which one has high toughness. and then you've got to explain that. Of course, it won't on the diagram say which one has high toughness and which one has high strength. That's just a blow up, make it a little bigger. I thought the last slide was a little small to see. Same information there. Endurance limit. We don't use that a lot in civil engineering, but it is a material property. Endurance limit is the stress level that you can repeatedly load something and not have failure occur. Mechanicals and aerospace guys are all about this one. How many times can I load, how many times can I take off and land with the wings on the airplane knowing that they go up and down each time, and how much they go up and down has an effect on how long they'll last. If they go up significantly and down significantly, then the wing's going to break off quicker than if they just have small vibrations to it. So this is looking at an endurance limit, and you do your testing, and you eventually see that you get below a point where no matter how many cycles I put against the material, if I say against 0.4 of the ratio of applied stress to strength, then I don't have to worry about how many cycles I have. The plane can take off and land as many times as we want, and we won't have a failure because of violating the endurance limit. If I start putting a load on here that's, say, 0.6 of the ratio of applied stress to strength, then I'm going to get 10 to the 2 repetitions. I'm going to start having failure occur. So I want to avoid that point and get down below that 0.4 for this particular material we see on the screen right here. Density and unit weights. That's the other thing that's a little bit challenging maybe for this exam. Most all the exam will be in metric units. So make sure you dial up your metric units. There is conversion table, I believe, in the review manual for you to be able to utilize to do that as well. But make sure you make sure you got in your head straight what density is and unit weight and specific gravity and how they move between all those once you're given one, and how to get to another one. There have been some examples or some questions as simple as, here's the specific gravity of this material, what's its unit weight? Real simple, real quick, real fast calculation. I have not really seen recently, I've had these slides for a while, I've not really seen anything getting too particular on different types of densities. It's getting a little too deep into the density concept. But we do have, depending on our volume that we're looking at for the materials, we can get different densities for the material. So we're going to scoot past this pretty quick. Thermal expansion, real common question to give you this. Here's a beam, here's a rod. We heat it up to this temperature. How much does it expand or contract? And here again, the equations are in the book. Just get the equations out. Make sure you got your signs going in the correct direction, and do the calculation. And there are the equations. Jumping in, so that's maybe the materials concept stuff. Like I say, it's stress strain curves. That's really what we're talking about there for the most part. Talk a little bit about steel production. Review on that. When we make steel, we're trying to reduce the iron ore we dug out of the ground into what's referred to as pig iron. Pig iron has very, very high carbon content. Very, very high carbon content. We'll process that some more, and we'll refine that pig iron into steel. Not necessarily the final product we're going to have, but it's getting close, getting down in that steel category. Low carbon contents at that point. And then we'll make it into whatever we're going to make it into. We'll make beams, we'll make columns, we'll stamp it into vehicle parts, whatever it might be, to make the final product. When we got pig iron, we're talking 4% carbon content. 4% itself is not a big number, but when it comes to steel, that is a very, very high number. That's a cast iron kind of condition. And any of you have had much to do with cast iron. When you hit cast iron with a hammer, it's going to crack, especially if it's hot. So it's very, 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 very brittle, and we don't like that in our steel. And we've got other smaller constituents in there that we'll try to remove as well during our process. In reducing from our iron ore to our pig iron, we're going to go into a blast furnace and heat the material, throw in extra carbon through coke, throw in limestone to help attach itself to the impurities there to get those out of the mix. Coke's going to help with the oxidation process, removing the iron oxides. Limestone removes the impurities. So literally just aggregate limestone we're putting in there. It's going to grab hold of all those impurities and float them to the top during this process. We're going to pull those off in the form of slag and technically throw it away from a steel making standpoint. We can use that in other applications. Put it in concrete, put it in fills and things of that nature if it's controlled correctly. And we take the molten iron, and typically it's decanted off the bottom of the pot so they don't contaminate it with any of this slag we have on top. And they'll sacrifice a little bit of steel in the pot just not to contaminate what they move on to the next level. So they'll decant it off the bottom and move on to the next process. Our whole concept there is getting carbon out of the material, getting carbon out. Two common furnace types, basic oxygen furnace, electric arc furnace. High energies here, big quantities of energy. Use a lot of energy to make these materials. Putting other materials in there like aluminum or ferrosilicon to help deoxidize the material. When we get oxygen out of there, and ultimately if we can get all the oxygen out of there, we call it a killed steel. Makes this good material when we can do that. Once it's made, it comes out of the bottom of that heating process. We'll turn it into ingots for transport to somebody else to reheat and process into different materials. Or if we have a continuous process, it'll go straight into processing and become whatever it was going to become, flat plate steel, whatever it might be. There's a diagram of the process. I'm not going to go through that in great detail so we can keep moving here. When we look at the carbon content, that tells us what kind of steel we got and what kind of application we can use it in. And if we've got this high carbon content, greater than 2%, very brittle, typically a cast iron application. We can have what we refer to as high carbon steel. That's at 0.8 to 2%. We're still very brittle, What we like in our structural engineering structural steel is that carbon content down around 0.15 to 0.27. Reasonable question. Carbon content of this steel that was just produced has a carbon content of 0.4%. Would that be an acceptable material for structural steel? Of course it wouldn't be, because it's got too much carbon in it. If we get too much carbon, we get brittle. We don't like brittle in steel because it doesn't give us a warning sign. We also don't want to be down around 0.1% because then we're too ductile and we can't get any control of our structure, and we'll get it drooping and sagging because it's too ductile. So we have a sweet spot in there, that 0.15 to 0.27%. An unusual condition seems a little maybe counterintuitive. You have the same modulus of elasticity for all these materials. The carbon content does not influence the modulus of elasticity. So you have the modulus of elasticity is the same for all of these. Heat treatment processes, don't see a lot on the exam that I've seen, example problems and things like that out of different books. But you need to know the processes and what each one of these does. Annealing, normalizing, hardening, tempering. I've seen questions where they'll say, you need to make a material that's this behavior when it's done. What would you do to it to make it that way? Would you just anneal it, normalize it, temper it, harden it, or would you do a combination of those? So and here again, it's just memorizing terms is what you're talking about there. Annealing, we heat it up and cool it down real slow. And when we do that, it helps our material, makes it a little more softer, makes it a little more ductile, and increases the toughness. So if we want something that's machinable, malleable, so we can make it form it into where we're going to form it into, and has some toughness, then we'll do this annealing process. Normalizing is not so much a process of doing something to the steel, but more taking behaviors out of the steel. And some of the processes we'll put stresses into the steel. In the manufacturing process, we can go through a normalizing process, and it takes those stresses out, relaxes everybody back to almost like a status quo, if you will. Hardening, if we've got bearings in a vehicle, we've got bearings in your motor, you got camshafts in your motor, you got things that you want to have very, very hard surfaces so nothing's going to scratch them, nothing's going to put any kind of abrasion to them. We want to harden that surface. And you go through that hardening process to make the surface hard. It does make the material more brittle in that process, and a lot of times we'll follow that with tempering to get our behaviors back under control a little bit. Tempering, we take things up to little to lower temperatures, not as high as this 850, 950. We're doing some of these other processes, and air cool the product back down again. Increases our ductility a little bit and increases our toughness when we're doing that. Let's skip right past that. That's actually the zone that we are interested in from a standpoint of structural steel. That's from about 0.15 to about 0.27. So when we're looking at structural steel, its behaviors versus temperature are inside that red box. And if we want to normalize it based on the carbon content, we got to get into these different zones up here. So if we want to normalize something, we need to be in this little box right up here. So we got to pick what zone we want to be in for our temperatures, and that's how the temperatures come about. There's a large intricacy in this diagram. Large intricacy in this diagram that a metallurgist really understands more than us civils will know. We can add all kinds of alloys to steel to help with its behaviors. We can add alloys in there to help with hardness or corrosion resistance, machinability, durability, strength. Depending on what we want to do, we can add different materials to it to get the property we like for whatever the application might be down the line. And there are a bunch of the different alloys that you can put into it and the properties that they increase. I haven't seen too much of any examples that are really going to go into that hardcore on the exam. Ultimate goal is the removal of carbon, and that's a reasonable question. When we're making structural steel, what are we trying to remove? Carbon. I kept that in there from the class. It's a lot of the different places we have different types of steel. We have different names for different components, things like that. Don't know that you're really going to see much like that on the exam. About making hot rolled sections, here again, I don't think you're really going to see a whole lot of that. Testing the materials, they can't ask you about tests. Really easy to ask you about tests. What does this test give you? What's that test give you? Or if you run this test, will it give you this property? Or will it give you that property? So make sure you're aware of some of these tests. Stress strain curve. There's a plot of carbon content for stress strain. And as you can see, as the carbon content goes up, we get more and more brittle behavior. Yeah, we get increase in strength, but we get that brittle behavior, which we don't like. No warning signs that we're going to get failure. So we really like that first curve, 0.19, and get a nice shape, nice design characteristics out of that. Sharpie V-notch impact test. We're getting toughness out of this test. Put the sample in there, drop that weight. You're measuring the energy it takes to break through that specimen. Gives us our toughness. A lot of times we'll look at this versus temperature, and we can plot toughness versus temperature and see how this material will behave in different environments. As would be intuitive, as temperature gets up, things get more ductile from a steel standpoint usually, and as things get colder, it gets more brittle. And you can plot that and see the change over time, and you can pick sometimes your material you want to have based on this property, because if it's going to be in a cold environment, you don't want it to be brittle, so you'll get a material that behaves better or more ductile in a cold environment. Rockwell hardness, this is measuring that hardness of the surface. Basically, it's a device that's spring-loaded. It's putting a dent in the surface, and depending on how deep that dent goes, tells us what the hardness of the surface is. Here again, it's just the surface we're talking about. And when you test it, people refer to what's the Rockwell hardness of that steel or that material. Corrosion's a big issue. They could ask something about corrosion. What do you have to have for corrosion to occur? They're not going to ask you how much it costs per year by any means. You got to have a cathode anode conductor and electrolyte. When you got steel, you got 3 of the 4 sitting right there. You got an anode, a cathode, and a conductor. All you got to do is have some kind of liquid. Moisture in the air is enough liquid to rust steel. If you go back and look some of the videos online on YouTube about steel production, during the production of steel, they are constantly blasting rust off the surface of the red hot steel because it is rusting the instant it's made. The instant it's made. And that's a challenge to deal with. So they're constantly blowing that off with hot air and hot pressure steam to keep that material off so it doesn't become incorporated into their into the steel in the steel production process. All kinds of different coatings you can put on, sacrificial primers. You can put on sacrificial metal. You can actually attach a piece of metal to your steel that corrodes faster than steel does. So the corrosion will occur there. You can bury, on pipes a lot of times they'll bury zinc or magnesium in the ground with a wire coming off of it attached into their pipe. So instead of the pipe corroding, the zinc or the magnesium will corrode. And you have to go out there periodically and replace those blocks because they do rust away. 4 states of moisture, getting into dealing with aggregates now, getting into dealing with concrete. And we've got dry, the only time that occurs is coming out of the oven. We've got air dry, that's some unknown moisture. It's not oven dry, but it's not saturated surface dry either. It's somewhere on the dry side of saturated surface dry. Saturated surface dry is when we got the surface just damp so it didn't get moisture on our hands, right? Just damp enough so the surface is just dampened. All the voids in it are filled. That's saturated surface dry. That's a known point. We can measure that. We can run a test and find out what that is. We can dry it in the oven. We can get dry. The air dried moisture content is whatever it is. It's less than surface saturated dry, but we don't know exactly where it is. We can run a moisture test and we can find out if we wanted to. And then we've got a moist condition. A moist condition is wetter than saturated surface dry. It could be just a % more. It could be a whole bunch more. You don't know where it is. It's really an undefined point. We know 2 points. We know when something's oven dried, and we know when it's saturated surface dry because we define those points. All those other 2 points can be a point in between anywhere in there. Another diagram showing the same thing, oven dried to moist as we move across through there. Saturated surface dry is being depicted there as having little to no moisture on these surfaces right here. But all our voids are filled out to the edge. That's saturated surface dry. So that's a point we can get the aggregate to and determine the moisture content and declare that that's the saturated surface state. If we're not filling up all our voids, we've got an air-dried condition. And you can see here we've got more water around the surface here than we know what to do with. That's some kind of a moist state. And of course, we refer to the difference between free moisture and the saturated surface dry condition, or the moisture, the difference between those two, between the moist condition and the saturated surface dry condition, telling us how much free moisture we have. Any moisture that's beyond what fills the voids is considered free moisture for our mix design when we're talking about concrete and aggregates. When we refer to as absorption, and this, here again, they're going to throw a bunch of terms at you. Absorption is, by definition, the moisture content at the saturated surface dry condition. So when I say what's the absorption of an aggregate, that's the amount of water it takes to make the aggregate just moist enough that the internal voids are filled, but I don't have free water on the outside surface. Moisture in excess of the saturated surface dry is the free moisture. It's extra water that can be utilized for something else in a concrete mix, let's say. That's important to us in concrete, and we will have a concrete problem we'll do here on calculating our mixed water here before the evening's out. And the concept is if we have free water, we have more water on the aggregate surface than the aggregate needs, that water will be free to mix with our cement and change our water-cement ratio, which is critical for us. If the aggregate's dry, the aggregate will get its moisture. The aggregate always gets its moisture. And it will take moisture away that could have been used for your cement and change your water-cement ratio. It also changes your workability. We have to have enough water in there for workability and handleability of the concrete. So if we're on the dry side, we won't have good slump values, we won't have good handleability, workability of the concrete, and we'll have problems. If we don't take this into account and we have extra water in the aggregate we pick up, then we're going to end up having a real sloppy concrete because we have too much water, and then that's going to cause us all kinds of other problems. Lower our water-cement ratio, which is bad, but also make it so aggregate can segregate out, and some other things of that nature. So we could have positive or negative free water, and that's what we're going to do in those calculations a little bit later on when we talk about Portland cement concrete. Calculating moisture content, it does sound very, very simple. The key is the bottom term in the denominator here is weight of solids. It's not total weight. It's not any other weight you can think of. It's the weight of solids because that's the constant in all our equations. And you can rearrange that if you want to get moisture content. But it's a very simple concept, it seems, but there's a lot of people getting mixed up when they start putting other terms on the bottom there besides weight of solids. And that's all about calculating the moisture content of all those different states. Specific gravity, they're going to have you work with specific gravity possibly in calculating, using specific gravity in a calculation. I don't know that they're going to sit there and ask you for specific gravities of different materials by any means. And that's a lot of memorization. Wood, I haven't seen a whole lot of questions on wood and timber on there. Just remember that one of the big keys, it's anisotropic. It's got different properties in all three directions. And the strength, modulus, thermal expansion, conductivity, any property you can think of is different in all three directions. And that's because of the way that the cells grow and the way the tree grows that makes it so it's different in all three directions. Moisture content is critical when you're dealing with timber and lumber. You'll get shrinking and swelling, very similar to what we had with the concrete and having free water and all that kind of good stuff. We've got the same concept in the timber industry. We've got bound water and we've got free water. I mean, depending on where the water content is in relationship to the fiber saturation point, tells us whether we're going to have shrinking or swelling at all. If we go above the fiber saturation point, we don't get any change due to increase or decrease in moisture content. If we're below it, then we get shrinking and swelling of the specimen. And we'll get shrinking and swelling of the specimen in all three directions, and they'll all be a different amount. That's why we get warping and things like that in our lumber sometimes. That's a diagram of those different quantities, depending on what direction you're looking at in the material. If you're looking at the long axis of the material, longitudinal axis, that's like 0.25% change in length for anywhere from 0% moisture content to 30%. So basically, any moisture content you want, the length of a piece of a 2x4 is going to change very, very little in the long axis. But if you start looking about the radial direction or tangent, if you get a difference between 30% to 0, you're talking about an 8% change in length. 8% change in length. Now, it's starting to add up real quick. So if you did have a stick of wood, and maybe it was manufactured at 20% moisture content, and it gets an equilibrium point of 5%, and you look at the radial direction, well, that's how much the shrinkage was at when it went up the line, got to this point. This is how much swell you just got, or you lost. It's shrinkage, sorry. It's shrinkage. If you went the other way, you'd be getting swell. So you realize that that's one of the challenges with timber and lumber. It's very, very anisotropic. Or the same thing, specific gravities of wood. Good to have a good feel for specific gravities. Lumber typically is between 10 and 60 pounds per cubic foot. The big thing you got to remember is it floats in water, so it's got to be less than water, right? We've got the same properties for woods. We have everything else. stress strain curve, you can get the modulus elasticity, you can get toughness, you can get all those kind of things for timber just like you can as steel or concrete or anything else. Timber has a greater tensile strength than it does compressive strength. Greater tensile strength than compressive strength, although we typically use timber only in compressive applications. But it is stronger in tension than it is in compression. Load duration, the longer you load a piece of timber, the more you have to worry about what kind of load you're putting on it and what kind of deformation it's going to get. I've been in buildings where the timber was 100 years old, had some pretty good sags in the ceiling just from its self-weight over 100 years of hanging there. And this diagram shows that very phenomena. If you were going to design something that was going to only be loaded for 10 minutes, you can use a higher design load than if you're going to design something that was going to be in place for 100 years. And that's everything quick on materials and aggregates. We'll pop up here next the show on Portland cement concrete, and asphalt concrete. And we will take a 5-minute break here. Get us a quick drink.